Okay, let me try another one here. This is from chapter 10, number 79. And this is about a ball rolling down a hill, then going around a loop here. And they say that the ball starts so that its lowest point is a distance h, and that means its center of mass is a little bit higher than that by some distance we'll call r, the radius of the ball, not to be confused with the radius of the loop it's going to go around here. And so the first part, A, is saying this. Well, what does it say here? What is the minimum height in terms of r such that the sphere completes the loop? Okay, so to complete the loop, you've got to be going fast enough that when you go around, and particularly here when you're upside down, you have enough speed that your centripetal force, so we're going to end up going back to chapter 6 on this, is enough to hold you up there. But let's start with the first part. I'll call it the conservation of energy part. That's the chapter 8, if you will. But there's also the other part, that the sum of all the forces have to equal to v squared over r towards the center of the circle when something goes in a circle. So that's our chapter 6. So I'll start here with chapter 8 and then say, all right, let's talk about the energy it starts with. So it starts with mg, and I'll call this its initial height. That would be h plus little r. And so that's the gravitational potential energy it starts with. It then rolls down the hill, gaining speed, then goes up the loop, losing speed, and then it gets right here, so it has some gravitational potential energy based upon how high it is. And so its height right here, of course, the whole loop is 2r. And don't forget to throw in chapter 9 here that the center of mass then is a little bit below that by a distance of little r. So that's why the height of it is 2r minus r. And then, of course, it's moving. So it has kinetic energy, and that's where the 1/2 mv squared comes into play, but also the 1/2 I omega squared, because it's not only translating, but it's also rotating. And so here's our, I guess, chapter 7, and here's our chapter 10 here, our new piece. And so we've got a lot of stuff here. We've got, the chapter 6, we got the chapter 7, we've got the chapter 8, and the conservation of energy is chapter 8. We've got the center of mass of chapter 9, and then this chapter 10. So this could be a hard problem, although they only listed as a blue one. But you've got to put all those pieces together, and that's really, I think, what makes this chapter hard. I think this one or the next one, but probably this one is the hardest one of the semester here, chapter 10, because again, we've got to make sure we realize that both things are going on, both a translation and a rotational energy. All right, well, if we maybe simplify this a little bit, this is an mg, h plus little r, and then this is an mg, and it's 2r minus a little r. And then where I can put things together is to say, well, the translational speed and the rotational speed are connected together, because in pure rolling, then, as something then spins around like this, the velocity tangential is its radius times its angular speed. And so if the object and this is important, rolls without slipping, there's a direct connection between its translational speed and its rotational speed. So I'm going to take advantage of that by putting in here for the omega, the V over R. And so right here, the omega, the V over R. So that would be a V squared over an R squared. So that's the omega squared. And then I'll also take advantage of the this chapter where we talk about here this moment of inertia. And so for a solid sphere, it's 2/5 mr squared. If you go back and look in the table there for the moment of inertia of a solid sphere. And I suppose I should emphasize that, you know, why am I picking solid? Did it say? Yeah, good. The first step there, a solid sphere, because there is the hollow one. So, you know, it depends. If it's hollow like a tennis ball, that'd be different than if it's solid like a baseball. But this one's solid. And so this can simplify a little bit, because right here, the 2's cancel and the R squareds cancel. And you end up with a 1/5 mv squared. And so a 1/5 and a half have a common denominator of 10, and that would be a 5 and a 2 in the numerator, so it's a 7 mv squared. And so that's, again, the conservation of energy. But then adding to this, the speed is connected up to here. So if I were to do a free body diagram at the top up here, then what would be pushing downward would be not only its weight, but also then the normal force. And so this is saying that the normal force plus the gravitational force is what is pushing towards the center of the circle. And so calling down positive here, I'll give that a positive down and a positive down, and then it goes towards the center of the circle, which is down. So all these are positive, but that's the chapter 6 I was saying about here. Now there's an important word here that he uses. He said the minimum value. So in other words, it's just going to make it. So in other words, if this had been, H had been really high, this would go around really easy and really fast. It would zip around, and you would have to have a big normal force pushing down, and it would, you know, make it around the loop only because the track here is pushing really hard on it. So this is a convenient way of saying what they're really saying is where would the normal force have to be? 0. Notice they're not saying the speed is 0. Because, you know, if you went too slow, if in other words H was too small, this would come up the loop and maybe get here and then kind of fall off and fall away and never actually get to the top and never make it around here. So that's kind of the key here is to make sure we don't set velocity equal to 0 at the top here, but we set the normal force equal to 0. Oh, and I should be careful back here. This R is the radius of the circle. Same thing here. So this R, the radius of the circle, would be the radius of this center of mass. So in our diagram, that would be the capital R minus the lowercase r, just to be clear there. And so this was probably a poor notation on my part here at the beginning. This is the radius of the circle. And so it's not the little r, it's not the radius of the ball. It's not even the capital R, it's not the radius of the loop, because the center of mass of the ball is, you know, the center of mass of the ball is going around a circle that is a little bit smaller than the radius of the circle. Okay, so putting that into here and then noticing there's an m on each side that cancels off, I can get a G big R minus little r when I bring this over is equal to V squared. And so now if I use that here, I then have this mg, and I've got the 2r minus the little r, then I got the 7/10 m, and now I can put in this V squared, which would be a G and a capital R minus a lowercase r. And let me go to another page here. But what I have so far then is this mg h plus little r, and the other side is an mg 2 big R minus a little r, and now I have a 7/10 mg big R minus little r, and the mg's show up on every term. And so I can get my h, and if I look at here, this is a looks like a 2r here, and then a 7/10 there, so that'd be 2.7r, capital R, so 2 of them there and 1 of them there. And then when I bring this to the other side, that'd make it negative, so that's negative 2r, and so negative 2.7r. And so there's the answer, although maybe I need to simplify this, and maybe that's why they made this a magenta one instead of a blue one instead of a magenta, because this is the true answer, and of course you would subtract a little bit, but they said go ahead and assume that the ball is small compared to the radius of the loop. So I think they're saying go ahead and don't worry about all the finer details that we worried about back over here. And so we worried about, it starting at a height slightly bigger and going around a circle that is slightly smaller. And we worried about all those only to drop them off at the end. So maybe we should have dropped them off at the beginning, and that would have made it a lot easier. And then it would have made it a blue problem instead of a magenta problem here. But that's part A then. What is the height needed to go around? B, I think, is a little bit harder even. And so let's look at B, because in B, they're saying here that you start with this thing at a height of 3r, and then it kind of goes around this loop here. And now they're looking at a point P right here, point P. That's not even the top. It's the, I guess, level with the center of the loop. And they're asking here for the components of the force. Let's see how it says. It says what are the components of the net force on the sphere at this point. And so maybe I'll begin with the free body diagram. And so here's my loop, and the little sphere is sitting right here. And it's going to go around to the top, and I'll just draw that much. But looking at the forces on it, there clearly is gravity pulling down, mg, and then there is the side of it in the normal direction, and that's going to be a clue because that is pointing towards the center of the circle. So knowing that the sum of all of our forces, I'll call that the x direction, have to equal to mv squared over r towards the center of the circle. And of course, remember this r then would be the capital R minus the little r. And so that would be so the normal force would be the push towards the center of the circle. But another one force, don't forget here, is there is traction, if you will. There is friction. And it may not be obvious, but the friction is in an upward direction. That's because as the ball comes around here, it's actually slowing down. The ball, if you can imagine, is trying to grab and grab the track, and it's pushing the track down, so the track is pushing the ball upward. It's a slowing down process here, and so it's trying to climb a hill. It's trying to gain some traction here, and it's trying to push itself forward up the hill, if you want to call that forward. And so getting the correct direction to this force may not be so intuitive there. But that would mean then the sum of the forces in the y direction, if we call up positive, would be this F going up and then minus this mg. And that would have to equal to ma. And in this case, it is, you know, slowing down. It is... I don't like to use the word de-accelerate, but it does have an acceleration, and it's a slowing down acceleration. It's, in this case, it would be a negative acceleration here. And so we need to find that value in order to figure out what the sum of the forces are in the y direction. And just kind of wondering what might be easier. I think maybe the x would be easier first. So I'll go back to that one, and then we'll come back to this one. But getting this one is a lot like we did way back here when we did the conservation of energy. And so I'll just say initial energy is equal to final energy. And so it's starting then at I'll just put it all down here, mg, and the height would be 3r plus little r for how high it starts up at the top. And then, as it goes around the loop right here, it is now has a gravitational of mg, and it's just r. There is no little r to add to it, because the center of mass of the sphere is actually at the same height radius as the loop here, and so that's its height. And of course, then it would have a translational energy and a rotational energy, just like it had before. And so I'll just write that as, again, mg, and then this is the 3r plus r equals. And then here's the mg capital R. And now we're back to this again, where we did the 1/2 mv squared for the translational kinetic energy. And then we've got to do the 2/5 mr squared. And then this could be written as v squared over r squared, like we did in part A, where, again, the 2 would cancel off, the r squared would cancel off, and you'll get your mgr plus, and then there's the 1/2 and 1/5, which makes the 7/10 mv squared. And I suppose I didn't need to redo all of that, because if we go back to part A, we could have just easily just started there and put in 3r right there and kind of worked it out. But I thought it might be just nice to do it again from scratch. Couldn't hurt. And so if I continue on here and then subtract this from over here, I guess I'd get an mg, and this r from here makes that a 2r plus little r equals, and we got the 7/10 mv squared. And why don't I just go ahead and, I'll just cancel an m, and move the 10 and the 7 over. So that's 10 over 7 here. There's a g. There's a 2r plus a little r equals 2v squared. And the force then in this x direction. And so the sum of the forces in the x direction, if you will. And so we'll come back to this picture here. So here's the x direction. So I'm going to add them together. And I'll go ahead and call that the positive direction here for x toward the center of the circle. And so that is the normal force. And as we said, would have to equal to mv squared over the r, which would be this big R minus little r. And then leaving the m and the big R minus little r alone here for a second, then there's the v squared. So that's a 10 over 7g and a 2r plus r. And I suppose then normal force, I'll just write this on the as a 10 mg over 7 here. And so let's see if I did that right. 10 mg over 7. And then over here, there's the 2r plus the little r, and then the big R minus the little r. But again, if we're going to do kind of that same rough approximation here, we can not worry about those, and then these end up also canceling, and there's a 2 here, so this becomes 20 mg over 7 for the force in the x direction. And then, of course, maybe the harder one here is what is the sum of the force in the y direction. And so let me come back to our free body diagram. We got started here on B. The sum of the forces in the y direction is the frictional force up minus the mg. And so sum of the forces in the y direction. So frictional force is up, gravity is down, and that would have to equal to ma. And of course, the other thing that makes this chapter hard, and so here's the hard part, is don't forget also that the sum of the torques equal to I alpha. And so we got this by saying this is the sum of the forces equal to ma, and so this is Newton's second law for translational motion. But we also have this, which is Newton's second law for rotational motion. So this one we've been doing since chapter 5, so I think you are probably feeling comfortable with that one. The big one, though, is back here, and so let's do the torques. And so the torques, which is the radius times the force times the sine of the angle between them. And if you come back here to this free body diagram, you'll see, for example, the force of gravity goes right through the center of mass. So the torque for that one would be 0 because R would be 0, at least for the gravitational force. And then likewise, the normal force is pushing straight through the center of it. And so in that case, I would say the R is the radius of the ball, and the force is the normal force, but then I would have an angle of 180 degrees for the normal force. So I would get no torque from these two. So what's really slowing it down is this friction or this traction here. This is the one that is causing it to slow down. And so for that one, when I say the sum of the torques, there is only one torque, and it's coming from the friction. So the radius would be the actual radius of the ball, so we've been using little r for that, so I'll continue. The force would be the force of friction, and so that's what I used a little f there in my diagram. And then the angle would be this 90 degrees. I'll come back to the picture here, but you can kind of see here's the R coming out, and then here's the F going up, and that makes a 90-degree angle. And so that's the sum of the torque, and that has to equal to I alpha. Now I should be, again, a little careful with my signs, because this is the first time, at least I'm showing you the, both Newton's second law of translation and Newton's second law of rotation. And we want to make sure we have our signs right. And so back here, we said up was positive, and so if we had an acceleration that was making it go faster, then we would have a positive number, and if we had something making it going slower, we'd have a negative number. And I'm sure that's what we're going to get. We're going to get a negative acceleration here, but we need to match this with the torque here. And so I say that then because if the torque was spinning the ball in a clockwise direction, that would make it accelerate upward. And the torque we have, though, is slowing the ball down. So this is really then, of course, a negative torque. Good. So I'm going to put a negative sign there. And that, of course, also means that our angular acceleration is negative, which is good because it's going to go with our negative translational acceleration. Okay, so this side really then becomes a negative RF. And the moment of inertia, as we've said already, is the 2/5 mr squared. R squared. And let me take advantage of the same thing that we did way back here on page 1, where we said there's a mathematical connection between the speed, translational speed, and angular speed. There is also the same mathematical connection between the translational acceleration and the angular acceleration. We've got to make sure we get our signs correctly, and that's why I was making a big deal about this negative here. And so this acceleration then would be an A over an R. And so now, if you simplify this, you can see that this R cancels with 1 upstairs, and then this R over on the left cancels with the remaining one on the right, and then you get your force of friction, and I'll move the negative over here, negative, is 2/5, and we've got our MA. And I like the sign here because, remember, A is, of course, a negative number. And then we've got the negative of a negative, and so my force is then positive here. Okay, but using then this rotation, and so this, like I said, might be the hard part of the problem because, again, this is what this chapter is all about, is about rotations. But also keeping in mind that rotations and translations are going on at the same time. And so let me take that and put it back over to here. And so in the case of the force of friction, I'll put a minus 2/5 MA. Minus mg equals to MA. So there is an M everywhere, if that really matters. But if I move this over to here, and so I'm going to take that A, I'm going to move it over to here, so it'll be a negative A, and I already have a negative, so that's going to make 5, I'm sorry, a 5 over 5, and a 2 make a 7. So negative 5/7 A is equal to G. Although now to get my answer, I've got my acceleration at negative 5 over 7 g's. Good. Now I think I'm almost there, because remember, way back somewhere, here it is, page 2, we said that the sum of all the forces in the y direction would be mass times the acceleration. Okay, so the sum of all the forces in the y direction then would be this ma in the y direction, and so that's my m, and then I have a negative 5 over 7g, and so that's my net force in the y direction, and my net force in the x direction is back there. Yay, good. I think I got it.